estimating mean mu when sigma is unknown. So we already know how to handle when sigma is unknown if we have a very large sample. Okay, so we did that one before. So especially this is going to be handy with a very small sample. Okay, so later we will discuss those details, but in general we are looking at the case where the sigma is unknown. So we need one extra assumption. The extra assumption is that initial population must be a normal distribution. Okay, initial population. So this is the theorem. Okay, so suppose x has a normal distribution. So pretty much this is the initial distribution. So say the x has a normal distribution with mean mu and the variance sigma square. So say you pull a random sample out of that and you figure out the x bar, the average. We already know that if this is normal, so x bar will follow a normal distribution regardless of the sample size, okay, with mean mu, and the variance is going to be this variance divided by n. So in other words, if you divide this thing minus the mu divided by the standard deviation will follow a z curve. So we already knew this part, okay? So now what we are going to do is that we are going to replace this sigma by the S value, which is the sample standard deviation. So the minute we replace this sigma by the S value, so what this theorem is saying is that this quantity is no longer is going to follow the z curve. It's going to follow a different distribution. That distribution is known as the t distribution. Okay, so t distribution with degrees of freedom n minus 1. So in other words, the sample size minus 1. Okay, that quantity is known as the degrees of freedom. So let us look at the properties of that t distribution. So the first property of the t distribution, just like the z distribution, t distribution is also a symmetric distribution around 0. So in other words, just like the z curve, this is also symmetric around 0. So then you might think that what's the difference between the t and the z? But there was a property with the normal distribution. You remember that the normal distributions within 3 standard deviations of the mean, everything has to be there. So that is not correct for the t. So in other words, for the z, if you're looking at this one as the z, when you go from minus 3 to plus 3, everything has to be there, very little left afterward, okay, above or below. But t, that is not the case. These parts are much larger than the z curve. So this is known as the upper tail, this is known as the lower tails. So these tails are a little bit thicker than the normal tails. Okay, so that's the t distribution. The z, always everything kind of within 3 standard deviations of the mean. Okay, so for the normal distribution. So the second property, there are many t distributions that depend on the degrees of freedom. You are going to get different t distributions. Okay, so they depend on the sample size. In other words, n minus 1, the degrees of freedom, you are going to have different t distributions. Say for example, if you look at the t distribution with the degrees of freedom 5, say that the black line is the t distribution with degrees of freedom 5. So if you increase that degrees of freedom, say if you look at the 10 or the 20, say for example 20, the purple line, that is the t curve with the degrees of freedom 20. That 20 curve go below that black curve. Okay, and since this is below here as well as below here, remember that is symmetric around 0. Okay, so in the middle has to go higher because the total area underneath that curve has to be 1. Okay, so that is a little bit higher, so like that. So when the degrees of freedom is getting larger and larger, like a 30 or 40, eventually that T curve is getting closer and closer to the Z curve. So in other words, the degrees of freedom 100 is going to be somewhat below, below this purple curve, but above this red curve. The red curve is the Z curve. Okay, above that, so it's going to go under that. So below again here is symmetric. Okay, so in other words, when the degrees of freedom is getting higher and higher and higher, the T curve is getting closer and closer to the Z curve. So just like the Z curve, there are tables if you look at any statistics book, at the end or in the beginning, you have that T table, just like the Z table. Okay, so now I'm trying to show you how to read those T tables. So in your book, the T table, towards the end, you have it like that. So this is different from the Z table. Actually, Z table, you have this area, the shaded area, from here to here. The T table, the shaded area goes like that upper tail, this area. So in other words, if this area is alpha, this is T. You remember the notation I mentioned? T alpha, the area to the right. So this T alpha. Okay, so the T alpha values are the values over here. Okay, in the table, those are the values on the x-axis. The very first column is the degrees of freedom. Okay, so once you know the degrees of freedom and once you know the area to the right of that value, when you look at the appropriate value, you are looking at the value on the x-axis. It's completely the opposite of the Z table. So in the Z table, inside here is the probability, the area from here to here, okay, in your Z table, okay. So that is different from that, okay. So in other words, the degrees of freedom, this is that area to the right, whatever that alpha, okay. So this is that alpha. So now, say for example, you want to find the A value. The A value, this is on the x-axis, such that the probability, the T more than A, the T distribution more than A equal 0.05. Okay, and suppose the degrees of freedom is 10. In other words, kind of later, this degrees of freedom is going to go with 11 sample size, 11 minus 1, okay. But anyway, so here, what happened is that now, so here the T distribution with degrees of freedom 10. So we want to find the value right here on the T distribution. This is the T curve. Okay. And leaving area to the right, basically 0.05. So since the degrees of freedom 10, you need to look at, you can read only this row. You cannot read anything else. You have to stay within that row. And the area to the right is 0.05. So 0.05 area to the right. So you need to look at under this column and that. That's it. So this value is going to be 1.812. Okay, so this value is going to be 1.812. So if the degrees of freedom, say for example, say you want, say for example, you're looking at 0.025 with the same degrees of freedom. So in that case, you are looking at 10 here, that 2.228. Okay. So if you are looking at different degrees of freedom, say for example, say 30. Okay. So in other words, sample size is 31 technically. Okay. So it's basically it's going to be, so if you are looking at a T with this, 0.05 is going to be the value underneath that, 1.697, T value 0.025, this value is going to be 2.042. Okay, so that's how it goes. So you can read all those values. So like this value goes like continuously like 30 and then going to jump into larger values. say for example like 120, something like that. So without even looking at your table, if you have to guess this value, what is your best guess for this value? These two values. You remember that when the degrees of freedom is getting larger and larger, this t table is getting closer and closer to the z table, right? So in other words, this value should be kind of close to the z table value. So with 0.05 to the right from the z table, okay, from the z table. So if you're looking at 0.05 here, and on the other side 0.05, so here pretty much within, this is 5%, this is 90%. You remember that I kind of told you to memorize two values. If you memorize it, so in other words, z, this is that z 0.05, goes with 90%. Okay, so this is going to be 1.645 and z 0.025. All right, this is going to be 1.96. Okay, so these two values pretty much should be close to those two values, 1.645 and 1.96. So let us look at from your z table. So from your z table, see that the one value with 0.05 right there, 1.658, 1.658, and the other value is 1.98. So it's very close. All right. So in other words, if you look at the very last row, actually in your table it says infinity. In other words, the degrees of freedom is very large. Okay. Some books actually gives these values, some like 100, 200, 500, 1000, something like that. Okay. But your book jump from 120 to that. So this value should match with that. Because this is the z table values. Okay, so this value got to be, if you look at that, the very last row, see 1.645 and 1.96. So that will match. Okay, so it's pretty much what happened is that, so that kind of after 30, these values are kind of close to the z table values. These values after 30, somewhat close. Okay, so in other words, that's one of the reasons in the beginning I said that after, like, people sometimes consider 30 is a big enough sample or something like that, but I will discuss that in later. One of the reasons is that, but when I get into the formula for the confidence interval in the next slide, next video, I will show you where that is coming from. Okay, so anyway, right now this is how you read the t table. Okay, so in the next video I will show you how to get the confidence interval for in general when the sigma is unknown.